All right, this week we're going to be talking about exponential functions and their graphs. We're not going to spend a lot of time on their graphs, um, just because, I mean, it's, you know, with graphing calculators and all that, it's pretty easy to graph a exponential function. But we are going to be talking about exponentials, how to simplify exponentials. We're going to talk about how to solve exponential functions when it's a one-to-one property. We're going to use exponential models to solve real-life problems. So the first thing we're going to do is definition of exponential function. An exponential function f with base a is denoted by f of x equals a to the x. So in order to be an exponential function, the exponent has to be a variable, okay? So that's what makes an exponential function, is when the exponent is a variable. Now, there are many rules for exponents, and I'm hoping we don't have to go through every single rule, but here are the rules. The product rule says that if the bases are the same, I better turn on my marker here so you can see what I'm writing. If the bases are the same, we add the exponent. So for example, x to the third times x to the eighth is equal to x to the 11th. The base stays the same. So if the bases are the same, you add the exponents. Quotient rule says that if the bases are the same, we subtract the exponent. So I have x to the fifth over x to the second. I end up with the x to the third. The zero exponent property says anything raised to the zero power is 1. Now, this is an interesting one because if I had x, y to the 0, some people would say, oh, your answer is 1. No, it's not. The exponent only goes to the y here. Now, if I had, so this would be x. Now, if I had x, y raised to 0, that means the 0 goes to both terms. Then my answer would be 1. So there is a huge difference there. You have to make sure that you understand what the exponent is on. Okay, if there's parentheses, then it goes to everything that's inside it. I've got the power rule that says that if I have a power to a power, so if I had like x to the second raised to the third, then you multiply the exponents. Okay, so that would give us x to the sixth. So that's the power rule. So these are just basic rules of exponents. When you have an expanded power rule, if you have an exponent on the outside of the parentheses, it's going to go to everything on the inside. So if I add like 2a to the third, that's going to be 2 to the third, a to the third. If you have an exponent on the inside, so if I had like 6x to the third raised to the second, well, that's going to end up being 6 to the second, and then that's a power to a power, so that's x to the sixth. Okay, so, and a negative exponent, if I gave you something like 3 to the negative second power, that really is the same thing as 1 over 3 to the second. And a negative exponent, if it's on top, it moves it down to the bottom. If it's on the bottom, it moves it to the top. So if I had something like 1 over 4 to the negative second power, that gives me 16. That would be my answer, because that would rewrite as 4 to the second, which is 16. So those are some real quick review, hopefully, of exponent rules. So here, like on your assessment today, it's going to ask you to rewrite or simplify some exponents down. Whenever you have an exponent and you're simplifying, you should not leave a negative exponent. So in this problem, I would rewrite this as 1 over y to the 7th. Here I would rewrite this as 1 over 7 squared, or 1 over 49. Here, if I reduce this, I know the bases are the same. So I can multiply the 4 times 2, so that would give me 8 times x to the 6th, because if the bases are the same, we add the exponent. Here, this would give me x to the 8th. Here, I have a power to a power, so that would be y to the 12th. Here, the 4 is on the outside, so it goes to each one, so that's x to the 8th, y to the 4th. Here, I have a negative exponent, so that would be 1 over x to the 6th. Here, I would rewrite this as x to the 9th over x to the 7th, but that would reduce down to x to the 2nd. That's this first type of problem that is going to be on the assessment this week. You're going to have an assessment where it just asks you to simplify some exponents down. So that's the first part of the assessment this week. Then there is a rule. It says that if the bases are the same, so we're going to be solving equations now. Okay, and this is the second type of problem that's going to be on the assessment this week. So if I give you something like 2 to the 5th power is equal to 2 to the x plus 2. Okay, if the bases are the same, we know that the exponents have to be equal. So all we would do if I was going to solve this problem, I would just go, oh, 5 is equal to x plus 2. Then I would subtract 2, so x equals 3, right? So if I put 3 in here, 3 plus 2, that would give me 2 to the 5th. 2 to the 5th is equal to, it works. So if you are solving an exponent problem and the bases are the same, you just set the exponents equal to each other and solve. Okay, so here's some examples of that. If I have 9 is equal to 3x to the x, 3 to the power x plus 1. Now some people would say, but Mr. Shanklin, the bases aren't the same. Oh, but I can rewrite 9 as 3 to the second. So now I have 3 to the second is equal to 3x plus 1. Bases are the same. I can set the exponents equal. So 2 is equal to x plus 1. So x equals 1. So if I put 1 in here, that would give me 3 to the second. Well, 3 to the second is 9. Oh, it does work. Now, this one you have to get a little tricky here. 1/2 x, I want to get a common base. I could do this two different ways. I could rewrite this as 1/2 to the x equals, and then 8, I could rewrite that as 2 to the negative third, couldn't I? 2 to the negative third is really 1 over 2, or 1 over 8. I'm not doing this right. I'm gonna just forget that happened because 8 is the same thing as 2 to the third, right? So you could write it as 2 to the third, and then 1/2. I could rewrite that as -1, can't I? Because that's going to bring it over. So that would be -3 would give us the 8. Okay, so sometimes it's kind of tricky. You've got to be able to change the bases. So here it says use the 1-1 property to solve these. Okay, so first thing I'm going to do here is I'm going to rewrite this as 2 to the third is equal to 2 to 2x minus 1. I've got common bases. So now 3 is equal to 2x minus 1. Add 1 to both sides. So 4 is equal to 2x. Divide through by 2, x equals 2. Now I can check myself. Just put 2 in here. 2 times 2 is 4. 4 minus 1 is 3. So that gives me 2 to the third. That is 8. -1/3 to the negative x. Well, can I rewrite that as 3 to the x? Because a negative just flips it over. And then the 27, I can rewrite that as 3 to the third. So x equals 3 for my answer. So some of them get kind of interesting. You just got to be able to make sure you rewrite the exponent, or so the bases are the same. Graphs of exponential functions. When you're graphing something like 2 to the x or 4 to the x, the coolest thing is, if you remember the 0 power. So if I was going to graph 2 to the x power, 2 to the 0 is equal to 1, right? So I know at 0, it's going to cross a 1. Then if I put 1 in there, 2 to the first is going to be 2. If I put 2 in there, that's going to be 4. It's going to be an exponential function will look something like this. Okay? Because it's going to grow exponentially. Now, this is a better graph table here. So the larger the a value is, it's going to go up a lot faster, because when you think about it, 4 to the first is 4, 4 to the second is 16, 4 to the third, you're at 64, so it's going to go way up. So when you graph an exponential function, it's going to look like this. Now, sometimes they'll come down like this. That is when the a value is less than 1. Okay, so if I had 1/2 to the x power, this is called an exponential decay. The problem's going to come down like this. If the a value is greater than 1, it's going to look like this. We call it exponential growth. When it comes down like this, we call it exponential decay. And we'll be dealing with that more in the future. Now, applications, there's a lot of different exponential functions. There's going to be 3 of them that we're going to use this week. This one here is called it's used in banking when you put money into a bank account. It is the amount of money that you would earn if you're compounding interest. Okay, P is the original amount of money that you put in. R is the rate at which you compound, or I'm sorry, it is the interest rate. N is the number of times you're compounding per month, and then T is number of years. So for example, if I said, I want, I have an example down here. Okay, so let's, oh, that's not what, I thought I saw an example. Okay, so here, it says you invest $12,000 at an annual rate of 3%, find the balance after 5 years with an interest compounded quarterly, monthly, continuously. Continuously, that one's interesting, so we'll talk about that, and simple interest. So quarterly means it's going to be compounded 4 times a year, so n equals 4. Monthly, that would be 12 times a year, so that's my n value. And it says t 5 for 5 years, so t is equal to 5 in both of these problems, well, in all of them. So I'm going to use my formula. A is equal to P 1 plus R to the n over, or to the nt power. Okay, so if I plug this in here, I'm going to end up with 12,000, 1 plus, and then my interest rate is 3%, so you got to change it to a decimal, so that's 0.03, over n, well, n is 4, because it's compounded quarterly here, and then to the nt power, so that's going to be 4 times 5, which is 20. Now, I don't have a graphics calculator here. I have a real cheapo one here, so I'm gonna try this. This is not gonna be good, I don't think. So I'm gonna go 1 plus 0.03 divided by 4. Let's see what that gives me. Okay, I'm gonna raise it to the 20th power, and that gives me. And then I'm going to multiply it by 12,000. If I had a graphics calculator, it would be a lot easier. I could just plug the whole thing in. So I ended up with $13,934.21. Okay, so if so what they're saying is if you put $12,000 in to the bank, after 5 years at a 3% interest rate, you would end up with $13,934. So how much interest did you gain? Well, guess what? You take the original amount, because you already started with that, and you subtract it. So you ended up with almost $2,000 worth of interest in 5 years. Okay, that's how it works. Now the second problem, if it's monthly, I would just put 12 in for n and 12 in for n here. Okay, and it's going to be very close. I mean, the answer is going to be very close. Compounding 4 times or 12 times a year. I mean, it's going to be a little bit more because you're compounding a few more times. It might be $13,942 instead of 34. But you guys can use, figure that out yourself. Now, continuously compounding, that's a whole different formula. That is called the PERT formula. A is equal to P E R T. So this formula you use if you ever compound continuously. E is just a constant, okay? And it's on your calculators. Most calculators have an E button. I don't even know if mine does, because this is like the cheapest calculator ever. I don't think it does. It doesn't. I need to get a scientific one. E is approximately 2.71. Okay, so if I wanted to find the compounding continuously, I would put in 12,000, E, and then the rate, 0.03, times T, which is 5 years. And then you would figure this out. You should get a better answer than this. It'll be a little bit more, not a whole lot. It might be 14,000, but compounding continuously is the most you could ever have. But this is what we call the PERT formula. Okay, so if you're ever dealing with compounding continuously, you want to use the PERT formula. Now, simple interest is just a straightforward P times 1 plus R to the T. Now, because simple interest, you don't compound at all. It's just simple interest. Now, you could use the same formula, okay? You could use the same formula if you wanted to, instead of using simple interest. If this one and this one are exactly the same, if n is equal to 1, and that's what simple interest means. It means you're not compounding anything. You're compounding it once a year, so n is 1. Well, if you put 1 in here, and 1 here, guess what you get? You get P is equal to 1 plus R to the T power. So all you really have to, I mean, you could use this formula if you wanted to instead of this one, but you have to understand that simple interest means N is equal to 1. And these formulas are exactly the same if N is equal to 1.